Jai Hind everyone. Today we are going to discuss the second part of arithmetic logic unit, that is the undersigned operand multiplication using combinatorial array multiplier and the sequential multiplier. So, I am Dr. Akhilesh Verma, Professor, Department of Computer Science and Engineering, Ajay Kumar Green Engineering College. Welcome you all for the today's lecture. Now, before we start, we understand that the arithmetic logic unit is a very important component of a computer system, especially the CPU part. The CPU has arithmetic unit, and the arithmetic unit usually performs the arithmetic operation like addition and multiplication, division. We have already discussed in the previous lecture that how to improve the arithmetic logic unit's performance, especially the addition part, using the fast addition approach, that is the look ahead adder CLA. Now, continuing further, we are today understand the process of multiplication and how to improve this multiplication process to be more optimized and fast. Now, in the slide you can easily see that we are having the multiplication of two numbers. We are denoting it as a multiplicand and a multiplier, and here we can see the both multiplicand and multiplier are written in decimal 13 and 11, and corresponding value is written in the binary form. Now, we are discussing this particular multiplication for the case of unsigned multiplication. Both numbers are unsigned, there is no sign in this two numbers. Now, you very well know and understand and have done in your paper and pen approach of multiplication, and you have seen that the multiplier bit is multiplied with the all the bits of multiplicand, and the partial product is kept below the place value corresponding to each multiplicand. Fine. Now, this is for the first multiplicand bit. Now, what we will do for the second multiplicand bit, that is this one, we multiply second multiplier bit with the multiplicand, and while putting the partial product we shift it by one bit towards the left. Fine. Likewise, we keep on doing for the partial product 3 and partial product 4 and shifting it towards left from the previous partial product, and after we have multiplied all the multiplier bits with the multiplicand, we got the 4 partial product. Now, in paper and pen approach, we add these partial product, okay, we add this partial product and we get the value here one by one for corresponding to each partial product. Fine, like this. Here we can see that the we are making a product of two n bit number, as we have seen in the multiplier and the multiplicand, and the sum multiplication of these two number is at most maximum consumes 2 n bit. So, this is a 2 n bit. So, this is n bit number and this is a 2 n bit number as output. So, in general we can see that the unsigned multiplication can be viewed as addition of shifted versions of multiplicand. So, basically we are shifting the multiplicand and adding it one by one in the previous partial product. So, this we have done in the paper and pen approach. Now, how to do it in hardware, that is the very important thing, and if we see the process here, we can see that we are adding the partial products at the end, okay, or alternatively we would add the partial product at each stage, whatever we can do one by one addition or we can do the addition at the end. Fine. So, what is the rule? Rule to implement this multiplication is very simple. If the ith bit of the multiplier is 1, shift the multiplicand and add shifted multiplicand to the current value of the partial product. That is fine, it is quite sound fair, and then we hand over the partial product to the next stage, fine. And if the value of partial product is product at the start stage is 0, because we are not keeping the value as 1 initially, it is kept at 0 because it is blank, fine. So, we can implement this using this approach of arranging the arrays of individual multiplying bit of multiplier and the multiplicand. If we see, there are cells here, okay. So, these are basically the array of multiplier, okay, bitwise multiplier, and these cells, these cells can be expanded and understood with this diagram. Here you can see in this particular cell, okay, in this particular cell, okay. So, this is called as typical multiplication cell. Here we are using one full adder. So, you know very well the full adder has 3 inputs, first input, second input and third input, and it has one output, okay, as a sum, another output as a carry, fine. Now, see, if is the first input, it is a bit of incoming partial product, that is the previous one. So, we are using the approach that is handing over the partial product to the next stage. So, the previous partial product is coming from the previous cell. So, the previous partial product is coming from the previous cell, and now here you can see there is a AND gate. Now, we very well know the AND gate is basically used as a multiplication circuit element. So, you can see the two inputs of AND gate, one is the ith multiplier and jth multiplicand bit, that is very important thing. So, when a particular input is given to AND gate, okay, it can multiply the multiplier and multiplicand bit. So, when it is 1 1, it will give 1, when it is 1 0, it will give 0. So, it is quite obvious that when you are multiplying the 2 bits, we will get the multiplication of 2 bits using simply by AND gate. So, this full adder is having 2 input, again the first input is from the partial product from the previous stage or previous stage cell, and the second input is the multiplication of the jth multiplicand and the ith multiplier bit. Now, full adder has 2 bits from the previous partial product and the current multiplication of multiplier and the multiplier. Now, certainly there will be some carry generated from the previous right hand side cell after adding all the bits. So, the full adder will have a carry in from the right hand side cells, fine. So, 3 bits partial product previous partial product plus the current multiplier, multiplicand, multiplication and the carry in generated from the right hand side cell. So, these all added together, it will generate the sum. Now, this sum can be forwarded to the next stage partial product, that is partial product I plus 1 stage, and obviously if these 3 bits are added, there is always a chance to get a carry out, and this carry out will go to the next cell to the left of this, and that will be behaving as same as carry in for the this particular cell we have seen here right now. So, if we see this cell and placed like a array arrangement, so that is why this is called as array multiplier, that is why it is called as array multiplier. Now, you can easily see from this that there are 4 cells, okay. So, you can see that the multiplier Q0, Q1, Q2 and Q3 is moving towards each cell, and likewise the multiplicand M0, M1, M2 and M3 is also moving downward, fine. Now, we can see here that the Q0 is also forwarded to the next cell here. Similarly, the multiplicand is also forwarded to the next cell here. How it is forwarded, we can see from this diagram, and we can see that the multiplicand bit is being used here, also it is being forwarded to the next stage. So, we can see this connection. Can you see this connection? Yes. So, you can see this connection. So, multiplicand bit is used here in the AND gate, and also this is being forwarded to the next stage through this bypass for using in the next cell down the line. Fine. Similarly, you can see that the multiplier bit is also used in the AND gate, but it is further forwarded to the next cell towards the left for the use in the adjoining cells. So, we can understand easily this particular path that we have marked here in bold, that they are basically a bypass to send the multiplier and the multiplicand bit to the adjoining cells of the array multiplier. So, we can easily see that the Q0, Q1, Q2 and Q3 will go horizontally towards the each cell, okay, and similarly M0, M1, M2 and M3 multiplicand will go down to the each cell. Fine. So, we can easily see that when M0 and Q0 are given to this cell, okay, and since partial product initially set at equals to 0, so it will add 3 bits 0, M0 and Q0, and certainly the initial carries we are setting as 0. So, it will add all these together, fine, and it will generate the partial product P0 and pass the multiplicand M0 here and multiplier Q0 here, and it will send the P0 down here, okay, and partial product P0 and the multiplicand here and the multiplier here. So, we can see that these two cells will now be executed after the first right corner cell is executed. So, data is available for this particular cell and this particular cell right now. So, we can see here that the partial product is being calculated like a flow from right hand side corner and to the down to the leftmost corner of the cell, fine. So, we can easily see that the partial product is not generated in one go, it is generated one after another. So, the results P0, P1, P2, P3, P4, P5, P6 and P7 will come after a small gap of interval, fine. So, this can be a one of the limitation of combinational array multiplier, that the output of the multiplication is totally depend upon how much is the size of this array, okay. So, it is quite obvious that we can also see that the delay in the multiplication will depend upon the size of multiplier and multiplicand bits. So, it is a 4 bit multiplier and 4 bit multiplicand. So, this is a 4 cross 4 16 cross array. So, it will certainly take 1, 2, 3, 4, 5, 6, 7 okay, order of time to get the final output, fine. Now, students, think about this, is this a right way or we can improve it further? Now, if we see the computer array multiplier here, it is showing that inefficiency, and inefficiency is terms of the delay, okay. And another performance factor is that due to the high gate count that we have seen that there are 16 arrays. So, and each array has these number of elements of arithmetic logic like full adder and AND gate. So, that will cause the high gate count, and that will be causing the size increasing when we are going for 32 to 64 bit multiplier. So, that was costly also, and also in terms of the heat depreciation. So, perform only one function, namely unsigned integer product. That is the last negative thing about this computer array multiplier, is that it can perform only unsigned integer product. If we have a signed number, can it do? No. So, to improve the gate efficiency by using mixture of combinatorial array technique and sequential technique require less combinatorial logic. So, going for this performance issue. We are now proposing and giving a better solution, and that will improve the efficiency by mixing two things. One is the concept of combinatorial array and the sequential techniques, and by reducing this by doing this by reduction of combinatorial logic. Now, if we can see that by the rule we are doing the multiplication, generating a partial product. If we see, this is very important thing, if the ith bit of the multiplier is 1, add the appropriately shifted multiplicand to the current partial product. So, what we have done, we have shifted the multiplicand towards m0 to mn minus 1 towards the left. We are doing this, fine. So, if ith bit is multiplied is 1, we add appropriately the shifted multiplicand to the current partial product, fine. So, if we see multiplicand has been shifted left when added to the partial product, fine. But can we think about another thing, another logic, adding the left shifted multiplicand to an unshifted partial product is equivalent, okay. So, left shift, okay, is equivalent to adding an unshifted multiplicand to right shifted partial product. So, what we are saying that we are not shifting the multiplicand. Earlier we are shifting multiplicand to left. So, what we are saying, we are not shifting the multiplicand. So, we are keeping the multiplicand at the same place, okay, but we are shifting the right hand side the partial product. So, partial product is added by shifting right hand side by 1 bit. So, it is same, either we fix the partial product and shift, either we fix the partial product and add with the shifted multiplicand, or we can do another approach that instead of shifting left the multiplicand, we can keep the multiplicand at the same location and add with the partial product by shifting it right, fine. So, this approach is proposed, that is sequential multiplication using 2 registers for doing that, and these are the shift registers. Here you can see we are having a n bit accumulator register, okay. It is kept at 0 initially, and this has a capacity to shift right, fine. So, the content of A0 can move to the q n minus 1 bit of the multiplier q, fine, and this multiplier q register has initial multiplier value, fine. Now, initially the register is kept at 0. Now, apart from that, we have 2 more circuit elements. One is n bit adder multiplexer that can be used to convert that array multiplier into a sequential multiplier. So, using the control sequencer, which fetch the bit from the rightmost of the multiplier, and it decides whether it is 1 or 0. If it is 1, the multiplexer will be given a signal to choose the multiplicand, fine. If it is 0, the multiplexer is given to select the 0 value to the adder. So, what will happen based on the control sequencer 1 and 0 bit, okay, that is coming out of the multiplier register, it will pass on the adder with multiplicand or 0. Now, this is a partial product value initially set to 0. So, the first input will be 0, and if it is first multiplier bit is 1 from here, so it will send the multiplicand here. So, the 0 will be added with multiplicand. So, m plus 0 will be added, and this will go to the this accumulator, fine. Similarly, if some carry is generated by this adder, it will be stored here, fine. Now, what will happen one after we shift this multiplier towards right, so we will get the same thing that we are doing here earlier in the paper pen approach. We can see here that the multiplier is taken value f1, then we put the multiplicand as same, and if it is 0, we put 0 and shift it. So, likewise we are keeping here the sequential multiplication using the 2 shift registers that has capacity to shift right. Fine. So, what will happen after the whole multiplier is shifted towards right? So, this accumulator and the multiplier together will have the whole result. So, this is the logic for this sequential multiplier. Fine. Now, we can see and do these examples by paper and pen to verify the concept, and this is example given for you. Please do practice at your home, and we can see here with this table, initially multiplicand is value this and the multiplier value is this. Fine. And the carry is initially set to 0. Fine. So, this is the initial value after we do the add and shift operation. So, the first value will be add and shift, then add and shift, no add, and then add and shift, and finally this array will contain the product. Okay. So, students, please tell me which approach is more efficient in terms of performance and also in terms of hardware resources. So, we can obviously see the hardware resources are definitely in this approach is not fair enough, and there is a one possibility of reliability. But the time consumption, if we see that the time consumption for this particular approach is almost same, but since the logic can be developed fast and also the number of gates that is the high gate count performs causes the delay, and there is by speeding the frequency we can increase the shifting operation to be done very fast. So, certainly the sequential multiplication using the shift registers, that is sequential multiplier approach, is much more faster than the array multiplier and with a high reliability. Thank you students, and keep listening this particular topic and understand the logics behind the architecture and the hardware, how it performs well. Jai Hind.